is the fourth module of Thermodynamics 2, and in this module we will look at phase and chemical equilibrium. So, the key word here is equilibrium, and this has to do with everything we learnt in the beginning courses, where we said that a system is in equilibrium, or rather thermodynamic equilibrium, if it is in mechanical equilibrium, thermal equilibrium, chemical equilibrium, and any other forms of equilibrium. And we invoke this idea of equilibrium for one very fundamental reason, that unless a system is in equilibrium, we cannot define its properties. So, everything that we have learned so far in thermodynamics, anytime we have assigned properties to the substance, we have implicitly or explicitly said that the system is in equilibrium. So, let us see what type of situations we have already come across. We begin with the simplest one from properties of a pure substance. So, if we said that we were looking at vapor, liquid and solid, and in each case some subclass of vapor was a gas, subclass of that was an ideal gas. And we said that if in a system we have any of these, any one of these, then if the pressure is same everywhere, the temperature is same everywhere, and the system has no, it does not change its state spontaneously, then the system is in equilibrium. But we also looked at another case where we had a liquid and a vapor existing in equilibrium. So, these were the phases, and now we are looking at a mixture of two, L plus V, or it could be liquid plus solid or solid plus vapor, that there is an equilibrium between phases. And the criteria we put there was exactly the same, that the pressure is same everywhere and the temperature is same everywhere. So, what we are saying is that two phases, say this is a liquid drop existing in the vapor of the substance, then the pressure everywhere in the gas phase and the liquid phase is the same, then this system is in equilibrium. So, this is what we will study now, as to what is the condition under which we will have this type of equilibrium, which we will call phase equilibrium with one component. We will extend this idea to a second case, where you have a liquid surface and above that is a gas, and we are saying that these two need not be the same. So, you are looking at now a two component system. So, this is different from the earlier system we are looking at, and we are asking what is the condition under which there is equilibrium, and in particular what we will ask for is, in a vicinity of the surface in the gas phase in this region, what is happening, and similarly in the vicinity of the surface in the liquid, we ask what is happening, and under equilibrium what can we say about liquid in the gas in this region and gas in the liquid in this region. So, this is looking at phase equilibrium, but for two components. So, that is the second category that we look at, but now what we have done in this case, we are looking at one component, then we look at two components, And thirdly, we will look at a gas mixture of two or more components. The simplest two component mixture comes to mind is air, and if we say that these are nitrogen molecules, and within that we have oxygen molecules, then this type of a system we have come across at every stage in thermodynamics. In the simplest case, when we were looking at properties of a pure substance, we modeled air as a pseudo-pure substance. We also use this idea to study psychrometry. But then we did not make it a pseudo-pure substance when we were looking at combustion. There we said that air is two types of molecules, O2 plus 3.76 N2. And we implicitly assume that as it is air, or even in the case of a reaction that is happening and there are elevated temperatures, what we are saying is that O2 remains O2, N2 remains N2, and they are not reacting with one another. So, in the chemical reaction, O2 could get consumed. So, this will get used up, but N2 stays as N2. What we will now look at is that if we do have this mixture and we then subject it to say very high temperatures, 3000, 4000 Kelvin, then these two will start reacting, and you will start getting formation of various oxides of nitrogen, which in any combustion process is very undesirable because it is classified as a pollutant. So, what happened here was that O2 and N2, instead of being inert and not reacting with one another, under some conditions they begin to react. And so, what we will have air at this type of a temperature is O2 largely plus 3.76 N2 very largely, but two things can happen. O2 can dissociate and form 2O, nitrogen can dissociate and form atomic nitrogen, and partly both of them can react and form a whole bunch of oxides of nitrogen. The question we ask now is, how can we predict that for a given temperature and pressure, what species we have, what will be the species concentrations, not just the major species, but these ones which occur in very small quantities, what about them? And then we will also extend that idea that instead of just looking at oxygen plus 3.76 nitrogen, we even ask the question that if we have CH4 plus O2, then we wrote a stoichiometric reaction, but well, what there could be many other possibilities that the atom balance is very much there, but it is not going fully to CO2 plus H2O. It could be possible that instead of forming all CO2, it could form CO and some of the oxygen could remain unutilized as O2. It satisfies conservation of mass. The conservation of energy can also be checked and satisfied. The question is which reaction will take place and to what extent. So, this is what we will look at is now chemical equilibrium. Where reactions take place and the system comes to a new situation, new state. So, this is what the scope of this module is. So, before we get into the physics of this, this is recapping again. We will understand what is the criteria for equilibrium and how can we determine system properties at equilibrium. This could be one component, it could be one component with two phases, it could be two components with two phases, or multi components which react with one another. So, these are all those possibilities that we will look at. So, let us see that some applications. A reaction like CO plus half O2 going to CO2 looks perfectly fine, but it is also possible that this thing, which is the reactants, could form permit many combinations of CO2 plus CO plus O2. So, in general, if we make this as 1 minus alpha, this becomes alpha by 2, then there can be a very large number of values of alpha for which this reaction is completely satisfied. So, what we are saying is that on this side we have cold reactants, and this side we have hot products, and many combinations of products are possible. Which one will be the most likely situation? This is what we want to know. Then there is dissociation at high temperature, that if you take diatomic nitrogen or oxygen or any other gas and you raise it to a sufficiently high temperature, it breaks up into its respective atoms. To what extent does this reaction happen? How much energy it takes in or gives out? This is what we are going to ask now. Then we have the same CO and O2 mixture going to CO2, CO and O2, but it could be from standard pressure and temperature, it could be going to any pressure and temperature. And we can add yet another factor into this whole thing. We say that along with the CO and O2, what if we also had say 5 kilomoles of nitrogen, and from what we have done so far, we say that this 5 kilomoles of nitrogen will also find their way into the products. So, this is the products, this is the reactants. So, will you get the same composition of CO2, CO and O2 if there were no nitrogen, or if there were some nitrogen, or the concentration of nitrogen could be different for different situations. So, that is another question we are asking. All these are relevant to combustion applications, whether it is a gas turbine combustor, whether it is a power plant, or whether you are burning LPG at home or a wood burning cook stove, everywhere these are the type of questions we would like to ask. A application that comes from two substances in two phases is your vapor absorption system. A typical one is ammonia plus water, and throughout the system we have different concentrations of ammonia in water. In one case we like to dissolve ammonia in water, in other case we like to drive out ammonia. So, the system in those situations can be looked at this way, that you have a liquid in which there is some ammonia and some water in liquid phase, and then in the vapor phase we have ammonia and water. So, here the ratio of these two could vary, the system pressure and temperature could be different, or what we want to know is at what condition will the system come into equilibrium. And if we know that one system and we say we want to go to another state of equilibrium, that will also be told to us by what we will learn here. But what we will not be learning in all these cases is the kinetics or the path by which the system got from here to there, or it got to this equilibrium in the first place. So, we are not going to be looking at processes, we are only going to be looking at the state. Another application is air and water. For example, this is a surface of water like a sea or an ocean or a lake or a river, and on top of that we have air flowing. So, this is air going here, and then we ask how much is the moisture going out from here, how does the air properties change. A very common example of application of this is in climate change models or monsoon models, where you like to predict how much moisture does the air pick up, and then we ask how does that moisture get transported, and finally how does it precipitate. And in this case, we are looking at a small region that encloses the surface, and we want to ask what is happening here and what is happening over here. Another application of the same thing is that water, instead of being a bulk liquid, is in the form of small drops like a mist or a spray, and there is air around it. And then we ask, well, what is this water, how does it evaporate into the air, and what happens to the pressure and temperature, and how much can it go, to the extent to which this process can happen. So, applications of this is like in spray cooling and in some type of evaporative coolers also. So, a modified form of this is also what we are looking at in evaporative cooling. So, this could be cooling towers of power stations or industries, or even the desert coolers that one uses in their homes. Another application of this is in hydrogen storage, where we have a matrix, a particular form of nickel, and we ask, this is got a lot of pores in it, and then we ask that if I expose this to hydrogen, how much of the hydrogen will go in and settle down inside this. So, what is the criteria that determines how much hydrogen a certain amount of material, in this case say nickel, can absorb? This is one of the techniques being looked at for hydrogen storage. Then we can also look at a gas liquid system, where you have a porous solid, and in the spaces in that we have a mixture of a gas and a liquid. And this is what you have in oil exploration and oil recovery, where you have oil plus gas, and this could be more than one gas species. Oil is of course not a pure oil, this is a crude oil with no fixed formula as such, and there could even be some water in it. And we are asking is what happens to this mixture in this sort of a thing when you try to take it out, or when you try to inject more hydrogen more steam into it, questions like that. So, this is a very complex multi-component system in two phases, but this is very crucial in all type of oil recovery and gas recovery processes. So, with that brief background about the applications, we will now go into the first part of the module, where we look at the criteria for chemical equilibrium. So, what we have done in some sense is started with the most complex of the various systems that we had just listed, and said that in chemical equilibrium with two phases there, how can we understand its equilibrium properties. And then if we say that, well, if there is no chemical equilibrium, then what happens, and that brings us to the simple case of non-reacting gas mixtures. So, that becomes sort of a subset of a reacting chemical equilibrium. So, we begin by writing a typical reaction and say, well, we will look at a point when the reaction proceeds in a very infinitesimal way. So, let us take a mixture. So, we have say a container in which we have some amount of one substance and some amount of another substance. One we call A, one we call B, and the mixture is nu A plus nu B, where nu A and nu B are the stoichiometric coefficients of whatever reaction would take place. It is not necessary that we always will have this, but there could be differences. But the point to note is that in any chemical reaction that takes place, no matter what the initial nu A and nu B, the number of moles of A and B are, say N A and N B, when they react, the reaction will always be in a stoichiometric ratio. So, if you do a very small element or a very small step and say, look, from this state there was a very small reaction where some of the A and B went to becoming N C, which is the and D, which are the products, then few of the molecules went from reactants to products, but the others did not. And that is what we are calling here, that this is written as epsilon, which is a very infinitesimal progress in the reaction. And we say that this reaction will always take place in a stoichiometric ratio. So, we will multiply everything by epsilon nu A times A plus epsilon nu B times of B molecule becomes epsilon nu C of product species C and epsilon nu D of product species D. So, after this reaction has happened, the system reaches a new state, and let us for the time being assume that the reaction has stopped. So, what we have in the container now is this mixture. We have this much of A left, this much of B, some of it has reduced 1 minus epsilon, this much of C and this much of D. So, you now have a mixture which has got certain amounts of each of the 4 species A, B, C and D. And now we can do one thing, having learnt the thermodynamics of mixtures, that we know that if I want to calculate the entropy of this mixture, where S mix is I for every species, which is the product of the number of moles of each species multiplied by its molar specific entropy. So, if we have to break this up, we can write this as N A S bar A plus N B S bar B plus N C S bar C plus N D S bar D. So, that is how we calculate the entropy of the mixture. So, we have reached a new state, and then we can say that the same sort of a infinitesimal reaction happens after this. Now, what happens? And we can write that also and call it a state. This is we can call it at a new state 2. This was state 1 where no reaction took place, and then we can come out to state 3, then a state 4, each one of which was infinitesimal changes from the earlier state. In reality, this may not be happening. What we are doing is we are just saying that if this were to happen and we come to a new equilibrium, we will now ask the question of what happens to, say, entropy. This is what we had done. So, like this, we let this reaction happen in many steps, and each step produces a new composition, and finally, all of A and B disappears and you are only left with C. So, here is what we can do now. We can plot on an axis where this is 100% reactants, which means this was only A plus B in whatever the stoichiometric coefficients were there. So, if you want, you can write there nu A, this side is nu B, and this side is only products, which is 100% products, which is only C plus D. So, you have nu C times C plus nu D times D, that is all. There is no A and B in this, there is no C and D at this point, and these are states where R keeps decreasing and P keeps increasing. So, R decreasing in this direction and products increasing in this direction. And on the y axis, we will plot the entropy of the mixture. And we will say that in this system, we have been given a fixed volume, fixed mass and its internal energy. So, what we are saying is that you have in this system the process that we have looked at, there is no heat transfer and no work transfer, but internal entropy change, this could happen. The second law tells us that under these conditions, this is the condition that the system must satisfy, that delta S of the system must be greater than or equal to 0. That means S mix in our case, say in state 2, state 3 minus mix in state 2, this should be greater than 0 or equal to 0. So, one step to the other step, what this law is telling us is that the entropy of the system must keep increasing. And what is the system? System is the mixture of all those 4 species. So, if we do all of this and do a calculation and calculate the mixture entropy at each one of these points, then at this point we will get some value there, here we will get some value here, like that we can get a whole bunch of points. And we see that this curve passes through a maximum. So, if we draw a curve there, so what we will have is this, and this is a point where there is a maximum. And what this plot tells us is that when we are going from this state to this state, the entropy of the mixture increased. This state to this state, entropy increased. So, in this direction, whatever steps we took until we reached this point, this was satisfied, ds greater than 0. That means, this process is possible. What's happening on this side is that when you go from this state to this state, entropy has decreased, here to here entropy has decreased. So, what is happening is that in this direction, this tells us that delta S is less than 0, and this the second law of thermodynamics requires delta S of the system to be greater than 0. So, what we are saying is that this curve is not possible. The system will not violate going from one point to other point in the process. It does not violate conservation of mass, it does not violate conservation of energy, but this sequence of events violates the second law of thermodynamics, and so this is not possible. So, what we are left with is that the entropy of the system will keep increasing until we reach a point where ds is equal to 0, which is this point. And once it has reached that point, it cannot go to this point, because then the entropy decreases. The second law does not let that happen. So, the system will stick here. And this is what we say, that the system has now reached a point where by itself it does not have any tendency to change, and this is the criteria for chemical equilibrium. And what we have just done with this thought experiment is to look at a system which has got a fixed internal energy, volume and mass, and there is no heat and no work transfer. So, this is a fairly restrictive family of processes for which we have seen that the second law tells us that you will reach a point where ds is equal to 0. This is the criteria for equilibrium. Now, what happens if the system does have heat and work transfer? Then we have to do a slightly different approach, and we say that now there is heat and work transfer. The first law statement tells us delta q is equal to du plus delta w, or delta q minus pdv is equal to du, because this work we said is only at the work done at the system boundary, and the substance is a simple compressible substance. And the second law tells us that ds will be greater than or equal to delta q by T. Now, delta q is finite. So, if we combine these two, we get a new equation which says that TdS is greater than or equal to du plus PdV. Or if you rearrange it, we get this expression that du plus PdV minus TdS is less than 0. So, this is the second law statement. Now, we will start working with some more items on this one, because this equation is a little bit longish and does not tell us too much in a very elegant simple way. And so, we invoke what is called the Gibbs function G, defined as h minus T s, or specific Gibbs function as h minus T capital T into small s. So, these are the specific properties, extensive properties. And so, we say that the change in the Gibbs function, which we will now differentiate this for a given temperature and pressure. So, now the only restriction we are putting on the system is that its temperature and pressure are practically invariant. Heat and work transfer is allowed, and internal energy can change, but we say that in a small change where T and P are same. So, this we differentiate this equation is dH minus TdS minus SdT. Then we further put dH as U plus PV. This is what we had from earlier, and this gives us this whole expression. This part is PV differential minus ds plus SdT. Because pressure is constant, this term will go to 0, and because temperature constant, this term goes to 0, and we are left with du plus PdV minus TdS, and this we have just seen a minute ago, that according to the second law requirement, du plus PdV minus TdS, this entire thing must be less than or equal to 0. And so, we get a condition that delta dg Tp is less than or equal to 0, and this is the second more important result that we just get, that for equilibrium dg at T and P, that Gibbs function change, has to be 0, and the second law requirement is that processes can only take place in a direction where change of Gibbs function is decreasing. So, what we are saying is that a chemical reaction proceeds in a direction of decreasing Gibbs function So, while earlier we had the entropy increasing, what we have now is a little more general expression that for equilibrium dg at T and P is equal to 0, and that reactions and processes can proceed in the direction where dg is less than 0. So, if we did the same thing that we did earlier, where we plotted entropy, now we do mixture Gibbs function plotting. This side is 100% reactant, this side is 100% products, and this side we are plotting G mix, and again the mixture Gibbs energy is number of moles of each product multiplied by its molar Gibbs function. And then we do the same thing and say that G mix, what is it at state 2, then what is G mixture at state 3, and plot that. Then we get this set of points as the ratio of reactants to products, reactants decreases and products increases. These are the points we will get, and then after a while, until we come to the products, it will again go up. So, this curve has exactly the opposite shape of the entropy curve, in that it goes into a minimum, and minimum is the point where dg is equal to 0, and it tells us that when you are going from this state to this state, Gibbs function is decreasing. So, dg is less than 0, which is okay by second law. When you go from here to here or here in this direction, dg is greater than 0, and these processes are not possible. So, again we have this set of processes over here, this is not possible. So, the chemical reaction proceeds in the direction of decreasing Gibbs function, and at a when the Gibbs function is minimized, this is when we have chemical equilibrium. So, that is a nice thing to have known now, that we are not restricting ourselves to entropy maximization, but a much more broader definition comes when you say that the Gibbs function is getting to a minimum. And so, we can say that an important conclusion that has come out is that for chemical equilibrium, dg at a given T and P is 0, and here there is heat transfer and there is work transfer at the boundary of the PDV type. So, this is an important thing that we have now learned, and what is the condition for equilibrium. And so, if we know the individual properties, Gibbs function properties of the species that comprise the mixture, from that we can calculate the value of G, look at the changes in different directions and say if there is equilibrium, or if there is a reaction that is going to happen, in which direction it will proceed. So, we can summarize this thing in two ways, that you will have for fixed energy and fixed volume and mass, ds u v m equal to 0 is the condition for equilibrium, and for spontaneous isothermal isobaric change of fixed mass. So, this is what we were saying, that T and P are constant in the absence of all work except boundary work PDV. We have equilibrium dg T P m is equal to 0. So, PDV work is there, everything else in the form of work is not there. So, we got the criteria that we were looking for. What is the criteria for a system to be in equilibrium? Now, we quickly revise how to get in both the cases the properties SI bar and GI bar, I being the species that we are looking at. SI bar was the entropy at standard state, at that means P0 pressure and T ref, integral Cp bar T ref to T final dt by T minus RULN Pi by P0. Pi is the partial pressure of the ith species. This is important to note. And P0 is the reference pressure, the reference state pressure. Usually 1 atmosphere. And we can do a little bit of derivations, we will not go into the details of it. And to get the molar specific entropy of each species at temperature T, again this is at standard state pressure P0. This is the standard state in specific molar energy at temp T plus RUT times ln Pi by P0. Again, this is the partial pressure of the species. So, with this, we can either calculate explicitly using these relations the values of this and this, or we can use the tables, where you can take these properties from the tables, and the change of the property is listed in a separate column, which you can take from the tables. So, this is exactly what we have done in looking at reacting systems. Now, let us go back and see a chemical reaction, which says that initially we have Na moles of A plus Nb moles of B going to Nc moles of C plus Nc moles of D. So, what we will do is exactly what we were talking of a few minutes back. What if there is an incremental change in this reaction, goes to a very small extent? That means, a very small number of moles of A reacted with a small number of moles of B in a stoichiometric ratio. And became C and D. So, this is what we were looking at. We have system in which we have put at any instant we will find some A, B, C and D, and we are asking what will happen when temperature and pressure are constant. Now, we have already seen that the equilibrium criteria for this condition is that delta G for the process should be equal to 0. So, delta G, dG here, if you look at this incremental reaction, this will be dGi at T and P, which is the number of moles of each species at that temperature and pressure and the specific Gibbs energy, molar Gibbs energy. So, this has to be equal to 0, and then we can further rewrite this as Ga bar dNa plus Gb bar dNb plus C and D equal to 0. So, these are molar specific Gibbs functions. Or they are also known as chemical potential. At a particular temperature and pressure. This is molar Gibbs functions and chemical potentials at Tp. So, this is an important property that is there, and we will have to come back and keep using it in solving problems. So, that is an important definition that we have now come across. What is G bar A, G bar B, G bar C? Now, we go back to the point that when the reaction proceeds in an incremental way, it will always do so in a stoichiometric ratio. So, this is what was happening, and the chamber need not necessarily have at Na, Nb, Nc and D in the stoichiometric ratio. So, these are here the stoichiometric coefficients. We are saying that actual infinitesimal changes are always stoichiometric under the assumption that there is always enough of each species present. What we mean by that is that it should not happen that in a very small change B gets completely consumed and it does not exist anymore. Then of course, the reaction will not proceed any further, but then what we are asking for is also being violated. So, we are saying that actual infinitesimal changes are always stoichiometric, and we are assuming there will always be enough of each species. So, dNa can be written as an incremental value of epsilon A minus epsilon nu A, dNb is minus epsilon nu B, and similarly C and D, where epsilon is the extent to which the reaction takes place, and we say this is very, very small, maybe like 10 to the power minus 6, 10 to the power minus 8, something like that. So, having done that, we write now nu C Gc plus nu D Gd minus these two is equal to 0. The minus sign because these are decreasing in quantity. So, this is our criteria for chemical equilibrium. And this could be for any reaction, any number of phases. So, this is a very broad definition we have now come across, that for equilibrium this is what we should have. If it is not satisfied and if Gibbs function decreases, the reaction will proceed. The Gibbs function is increasing, it's reached, it's not possible. So, nu C G C bar plus nu D G D bar minus nu A G A bar minus nu B G B bar equal to 0. This we can write as a summation. This also can be written as a summation, and that is a more compact form of this expression. The next thing about chemical equilibrium is that it is not always that A plus B always goes to C plus D. At any instant the reverse is also happening, that some amount of C plus D is reacting to become A and B. So, A plus B going to C plus D, this is what we call the forward reaction, and C plus D becoming A plus B, this is the reverse reaction. So, even when we have equilibrium, that means there is no more reaction taking place, at that state also you would have A, B, C and D in the system. So, these are say A and B, and then we have C and D, and at the macroscopic level this is equilibrium, but at the microscopic level something else is going on, in the sense that some A and B are reacting to become C plus D, the same time some C plus D are reacting to become A plus B. And in equilibrium the rates of the forward and the reverse reactions are the same. So, at the overall level we see the same concentration of A, B, C and D. So, in that sense chemical equilibrium is not a static equilibrium, but sort of a dynamic equilibrium. It is always reactions going on, but at the overall level the amounts are constant. So, if the forward reaction, which is this direction, equals the rate at which the reverse reaction takes place, we have equilibrium. Otherwise, the reaction will proceed in the direction of decreasing dG at that temperature and pressure. Okay, so, this is the next thing we realize, that chemical equilibrium is a dynamic situation. So, we have now got one level of criteria for what is chemical equilibrium and how a reaction will proceed until it gets to chemical equilibrium. Now, we will spend some time looking at the Gibbs function, because then this will help us to further refine our equilibrium condition and come up with a little more elegant solution. So, Gibbs function, you can define it as in two parts like we did for entropy, which was the or enthalpy of formation. So, we will now look at Gibbs function of formation. So, this is G 0, which is standard pressure, P 0, T is the temperature, and this is the reference temperature. So, G 0 of F is the formation Gibbs function, which is like we had earlier H 0 bar F. What is the Gibbs function in that for the same situation for the ith species at that temperature. So, we write that G F, the formation Gibbs function, is defined as G I 0 or T minus summation of nu j hash G 0 j T, where nu j hash, this is the stoichiometric coefficients of the elements that are required to form the or form 1 mole of the compound of species I. So, what we are saying here is that if I want the Gibbs formation function, formation Gibbs function for say water, then we are expressing this equation in terms of this, which is H and O. So, by getting the Gibbs function for H and O at that temperature and pressure in the right stoichiometric ratio, subtracting it from what we have at T, we get the formation Gibbs function. So, this can be further modified and we can express it for a gas state that G0 of A at T is equal to G0 of A at T plus RUT ln Pi by P0, which was the expression that we had earlier, but now what we have done is written it for species A, where Pi, this becomes Pa, Pa being the partial pressure of species A in the mixture. P0, remember, is the standard state pressure. So, this should be P0 here. And now we go back to that equation that we had written earlier, which was nu C G C bar plus nu D G D bar minus same thing for the products is equal to 0. And we note that Pi by P, now P is the total pressure of the mixture, not to be confused with P0, which is the standard state pressure, and Pi, which is the partial pressure of the ith species. So, if you have a mixture of gases only at total pressure P, then Ga becomes, we can write the earlier equation in terms of the numerator, where we write Ya times P, which is the total pressure, and then using this expression we can calculate the Gibbs function for the mixture. So, what we do now is to combine two things, that this is now our definition of the Gibbs function for the mixture. Two entities are there, the number of moles of each species and the product with the Gibbs function of the species. And for fixed temperature and pressure, we require that dG mix should be equal to 0. So, what we will do next is differentiate this term. So, we will have in one case this is constant, this is changing, plus this is changing, this is constant. So, we will get two terms, and the sum of those has to be 0. So, this is what we have done here, summation of dNi times GIT plus summation of Ni times dGT, this is equal to 0. So, here we are saying that both these are in the summation bracket, and this came about from the fact that dG of the mixture for equilibrium is equal to 0. So, we can see that this term we will get ln Pi coming up there, the change in that from this part, this will be equal to dPi by Pi, and since we know that dPi is equal to 0, total pressure is 0. So, this term will disappear. No, this term, rewrite it this way. So, we have dG mix at a temperature T equal to 0, which is dNi Gi Ti bar plus RUT ln Pi by P0. And with number of moles of each species being infinitesimal change from its stoichiometric ratio, we can further write this dNi in terms of nu and put up a to summation there, that this is nu I Gi0 bar T for reactants with a minus sign plus products equal to RUT into a product, because all these things will now get added up and the logarithm becomes the products. So, this will become Pc upon P0 to the power nu c times P d upon P 0 to the power nu d divided by P a by P 0 to the power nu a into P b by P 0 to the power nu b. So, this is what this term in the brackets is going to become. And now, when we simplify this, we can say that delta g t at 0 is summation of nu I into this minus for the reactants the same thing. And then, since we got this product coming up there, we now define this as a new entity, which will be a great help and has a lot of other significance in chemical reactions, that this is the equilibrium constant K p defined as this ratio that we wrote a few minutes back. In the numerator, we have the products, and the denominator reactants. So, we have now come to a point where we got much information about chemical equilibrium. We said that dg equal to 0 is a reaction definition for equilibrium, and reactions can only proceed in the direction of dg decreasing. This is one important thing we have learned. The next thing is we came across now what is called the equilibrium constant. And before that, we came across a lot more treatment and the importance of the Gibbs function as something that is relevant for chemical reactions. So, we have reached an important point in our discussion of having defined what is the criteria for equilibrium and why the criteria from entropy was not adequate. We invoked the Gibbs function and came up with the idea of a equilibrium constant. So, we will conclude this lecture here, and we will pick it up in the next lecture and start looking at the equilibrium constant and its implications in more detail. Thank you.